In the last several videos, we've been looking at what I've referred to as the preamble to the second isomorphism theorem for rings. In this particular video, we're going to start working on the proof of that theorem. And the first thing that I want to do is I want to look at a statement of the second isomorphism theorem for rings. The second isomorphism theorem for rings says that if we let R be a ring, and S is a subring of R, and I is an ideal of R, then this particular quotient group and this particular quotient group are isomorphic to each other. Now, this is a pretty dense statement, and in the preamble, what we've been doing is we've been working on the pieces of this statement. And so I kind of want to review what we know about the preamble. And in the preamble, we showed the following stuff. We know that S plus I is a subring of the ring R. And in fact, it's the smallest subring that contains both S and I. We know that I is an ideal of R by the main hypothesis of the theorem, but being an ideal of R and a subset of S plus I also implies that I is an ideal of the subring S plus I. And so the quotient group S plus I mod I exists. And I'm going to let that be that kind of a circle. And so we're going to think about that circle as being S plus I mod I. And I know that that particular quotient ring exists. I also want to remind you that we worked on the other side of this diamond shape as well. We know from the main hypothesis that S is a subring of R, and in the preamble we proved that S intersect I, it is a subring of R, I, S, and also S plus I, because it's a full-fledged ring and it's a subset of all of those guys. But more importantly, we proved that this particular thing is an ideal of the subring S. And because S intersect I is an ideal in S, the quotient ring for this side of my diamond also exists and is well defined. And so this blob is going to be referred to as S mod S intersect I. And what the statement of the second isomorphism theorem says is that these two quotient rings are isomorphic to each other. Now, in order to prove that they're isomorphic, we need to find a map phi that goes from one of them, and I'm going to let it go from S plus I mod I to S mod S intersect I, and we need this map to be a one-to-one onto ring homomorphism. Because in that particular case, our map will be a ring isomorphism. So we want phi to be a ring isomorphism. And that will imply that the domain of phi, S plus I mod I, will be isomorphic to the target set, which is S mod S intersect I. Now, in order to come up with a good idea of what map to use, we need to look very carefully at the elements of the two sets that phi is supposed to be mapping from and to. So let's turn our attention to looking at the elements of the quotient ring S plus I mod I. Well, S plus I mod I is just the set of left cosets of I with representatives inside the subring S plus I. And so the elements of this particular quotient ring are going to look like x plus I, where x belongs to s plus I. But that's going to tell me that x itself is equal to some little s inside s plus some little a inside I, where s belongs to s and a belongs to I. So what does that tell me? That tells me our typical element x plus I is actually going to look like s plus a plus I. And I know how to deal with that kind of a coset representative. That's going to be s plus I, a plus in the quotient ring, a plus I. But the only thing is a is in I, so a plus I is the same thing as 0 plus I. In other words, a plus I is just the 0 element inside I, and so x plus I is really just s plus I, where s is inside the subring S. In other words, what we have shown is we've just gotten done showing that s plus I mod I is equal to the set of left cosets of I with representatives drawn from the subring S. In other words, s plus I mod I is nothing more than the set of things that look like little s plus I, where little s is pulled from capital S. Well, okay, now let's actually think about what do the elements of the target ring S mod S intersect I look like. So now we're going to look at the elements of S mod S intersect I. Well, again, S mod S intersect I is just a set of left cosets, but this time it is the left cosets of the ideal S intersect I with representatives inside the ring S, the thing that we're using as our big set. In other words, the typical element in this quotient ring looks like S plus S intersect I. Now I kind of want to put those two things together, so let's actually put them together. Elements in my domain ring, S plus I mod I, they look like little s plus I, where little s is pulled from the subring S. And the elements in my target ring, the target ring is S mod S intersect I, these guys look like little s plus S intersect I, where little s is pulled from S. So there's an obvious candidate to try for our hopeful ring isomorphism. So the obvious map to try is, let's call him phi, and phi is going to go from S plus I mod I to S mod S intersect I, and he's going to be given by, let's send S plus I to S plus S intersect I. In other words, this is what phi is going to do. So the obvious map to try is phi should send S plus I to S plus S intersect I. And I want to end this particular video with the question, is phi a ring isomorphism? In other words, is phi, and I want to clean my eye up there, is phi a ring homomorphism that is one-to-one and onto?